Hey everyone, CyberCDH here. Hope you're doing really well. Today we are going to take a look at Sunburst Malware. This is the malware responsible for the SolarWinds compromise, which is all over the internet right now, has organizations just running wild with incident response. Absolutely crazy time to be in the cybersecurity industry right now. Super fascinating. We have a nation state adversary who's compromised probably the biggest global supply chain you could imagine, compromising hundreds of thousands of organizations potentially with an amazing piece of malware that I'm going to show you the tools, the tactics, and methodologies that I use to crack this malware open, perform some initial analysis. You can scrape some of the malicious behavior, some of the IOCs from this kind of malware. Super simple to do. You just need the right methodologies, the right tools in place as well, and the right pointers. And hopefully that's what you're going to get from this video. Key takeaways though, this is a very patient piece of malware. Whoever's written this code is well resourced and very, very focused. This is an adversary with state-sponsored backing. This is just crazy, the level of code sophistication that is at play here. We've got a compromise of a software update lifecycle for one of the biggest platforms on the planet. That takes some reconnaissance. It takes a lot of ingenuity to break into that kind of environment. And there's a lot of nuances around how the bad guys may have achieved that particular goal. Also note as well, I'll link a few really interesting, fascinating blogs in the description of this video. But note that the SolarWinds compromise appears to be not the only infection vector by this particular threat actor. And you can imagine somebody who is as well resourced as whoever it is behind this SolarWinds compromise is well skilled at compromising other areas of organizations as well, other pieces of infrastructure, which is widely used. So expect more from this story to be developed. This is super fascinating to be in cyber threat intelligence right now. And in the malware space, we've got a lot of moving parts to get into. So we're going to dive in, we're going to crack it open. I'm going to show you the kind of research that I've been doing so far. Hopefully you can get involved, contribute in the community, start talking about how we can better protect ourselves from this kind of stuff. And I really look forward to it. So without further ado, let's dive right in. All right, so now we are using DNSpy. DNSpy is the tool that you want to disassemble and analyze .NET code. So this particular malicious DLL that we're analyzing, which is picked up from FireEye's indicators of compromise, grabbed one of the hashes, grabbed it from one of the online public repos that someone has ran it through. Fantastic. Download the sample. We've now got it in our virtual machine environment. DNSpy is where it's all at now because this is a .NET piece of code. And the beauty about .NET is that you can decompile it and see the true source code, the actual source code that the bad guy has written. And in this particular case, usually what you would see in this particular case is, the bad guy, you would decompile it and you would see that the bad guy has obfuscated everything. They've packed it. They've, made it really hard to analyze. Well, guess what? These adversaries were looking to blend in and not make any noise and not make their code stand out and look malicious. All of their malicious behavior has to fit in with the rest of this DLL because what they've injected into this DLL is only a small part of what this whole platform is designed to execute. So if you read the blogs, and you should definitely follow along, right? So real top tip for anyone analyzing any kind of malware. If someone else has already done research on the malware that you're looking at, follow along with their blogs, have a look through their research and compare and contrast. So if the stuff that you're looking at matches or differs slightly, then at least it gives you a real good starter for 10. And in this particular case, the analysis from FireEye is second to none. So let's go back here. and into our Chrome window. This is the blog I'm talking about. This is the blog that I will be linking to in the description of this video as well. The threat research from FireEye is just insane. It's just an amazing amount of research they've pulled together in such a short space of time. Also dealing with the incident response as well, their own incident response as well. So it gives you all of the details here about the malware, detection opportunities of how you go hunting for it, information about its domain generation algorithm, its network C2 infrastructure, the commands that this malware has built in, all the rest of it. We've got loads of stuff here, loads of really good points that we can go looking for, and loads of analysis techniques as well. So definitely follow along with the research that's already been undertaken. So back to our virtual machine here. What we want to look at here is, if you have a look in this Orion Improvement Business layer, this whole class of methods is what the bad guys injected. And really well, if you have a look at the rest of this code, look at all of the naming conventions of the other classes, other objects, other functions, everything within here, you can see that this just blends in perfectly. And we've got this initialize function. I guess it doesn't have to be called initialize, but we've got this initialize function, which is the first function that gets invoked by, or the first malicious function that gets invoked, I should say. And the reason why you know that, if you right click initialize and click analyze, you get the analyzer window up here, and you can see what calls the initialize function. And you can see what calls it is this call here to refresh internal, which is held in this particular portion of code. You can double click this and jump to it. And so you've got this little if block here in a try catch block in the code, which says it will start a new thread and it will call this initialize function and start it. And then this refresh internal, in turn, you could dig down what uses this. Well, it's this refresh object or method, and that's in turn called by the inventory manager start method, etc. So you can go through the whole tree of what process, what is the parent call to the process that we're interested in, or the method that we're interested in. So let's go back to initialize. So this gets invoked by these parent routines here. And the first thing this malware does, we said before that this malware is stealthy. Well, if you look, we're in a try-catch block, and there's no exception to the try-catch block. So if this fails for whatever reason, it's going to fail. It hasn't got a backup plan. And we've got a load of if blocks here, a load of if conditions that have to be met. Notice we don't have any else clauses. So again, if any of these conditions fail, nothing's going to happen. And this malware is quite happy to sit there and do nothing in particular circumstances. And so we're not going to analyze every single line of this. We're going to show you some interesting features. So the first thing it does, you can see here, we've got this weird hash, this weird string of numbers. Well, we've got a call here to get hash. So if get hash and then process.getCurrentProcess.processName.toLower, well, even without looking at that process, that function, even without going into it, you can guess that it's going to get the current process name. It's going to convert it to lowercase, and then it's going to get the hash. And we don't know what get hash is at this moment in time, but we'll look at that in just a second. So it's going to get the hash, and then it's going to compare it to this value here, this unsigned long value. And if it's the same, then it's going to execute. If it's not the same, ain't doing nothing. It's going to do absolutely nothing. So it has to match a particular process name. Interesting stuff. So if we go back to FireEye's assessment here, so we've got their signatures that they've released on GitHub, and they've got a load of hashes, and we'll cover this in a bit more detail in just a second. But you can see that particular hash is maps to this string here, SolarWinds.businessLayerHost. So it's looking to make sure that their process name matches that particular string. If it doesn't match it, ain't running. And how does it generate a hash? Well, let's have a quick look into get hash. You click on it, and DNSpy will take you there to the function. I've never heard of this function before, and it was definitely a new one on me. But this is looks like a relatively simple hashing routine. You take a string as an argument. You have this weird big long number. For each byte in the string, you XOR it, and then you multiply it by this constant, and then you XOR it with another constant as well, the super big long number. So a bit of a weird hashing routine. I have no idea what it was all about. And so the first thing I did, I saw a few of these constants and I was like, oh, this one looks interesting. I'm just going to Google it. And so I'll take the UL off the end. I'm just going to Google it. And the first thing that comes up is Fowler Nolvo hash function. I still can't really pronounce it. I don't really know what it's all about. But this FNV function is a hashing algorithm. And you can see here's the kind of pseudocode, and it's basically what we've seen there. So we've got a loop over each byte in a string. We get a hash being XOR by a byte of data with returned hash as well. And, maybe the bad guys have added in a funky XOR as well, just to make it their own. Who knows? But this is the implementation of that particular hashing routine. So super simple. That's what it's doing. Click on back. We'll go back to where we were in our code. So it's going to hash the current process, compare it against that static hard-coded hash, and if it matches, it's going to move on. Next thing it does, it takes the current, it takes the last write time of this particular binary, of this particular DLL, and it's going to just store that in last write time. Then it picks a random number between 288 and 336, and it does a date time comparison. So you can see the next line here is an if condition, and it takes the date time comparison of the last write time of the binary versus the number of hours here between 288 and 336. So 288 hours is 12 days, 336 hours is 14 days. And so it's going to check to see whether the date time now is greater than or equal to 12 days, 13 days, 14 days, whatever, or any hour in between that. And so what that means is, in real terms, this malware, once it's made sure that it's got the right process name, it's now going to sit there and do absolutely nothing for at least 12 days and up to 14 days. And it's going to make sure that it's sat there and done nothing before it does anything else. So again, if someone's inspecting this malware, if someone is inspecting the code, if someone's running the code to do some kind of testing, maybe what have you, well, you probably won't leave it running for 2 weeks. And so this malware, super stealthy. The first thing it does is it sits there and does nothing. And it does that by just calculating these very simple values. Then it creates itself a name pipe. Then it does some other stuff here. Read report status, delay, a little bit of a delay, calls to this get IP global function properties, whatever. You can click all of these and dive right in. You can go down the rabbit hole into analyzing this malware. And really, there's some meat on the bone here with this update function at the end. So literally the last subroutine here that we're going to look at before the instance closes, as you can see in this block of code, is really where there's some quite meaty stuff to get into. So click in update and we can see what it's all about. So again, we're not going to reverse engineer every single line of this. The idea of this video is to show you how to get to this code so you can perform your own analysis. I'm in no stretch, shape or form a professional coder. I've been able to understand every single line of it, but you may want to pick this apart line by line. You may want to just look for interesting stuff. And for me, those hard-coded strings of hashes, those FNV hashes, they were definitely interesting. And this is something that we'll talk about in just a second in a bit more detail that FireEye have done a bit more digging on as well. So here we're sat in a while loop. A bit further down the code, we're sat in a while loop here. And a while loop, we've got an if condition where we've got these track processes. So if not track processes true, so basically if the return from a call to track processes is false, then it's going to do all of this stuff in this if block. So we want to know what's in track processes. Again, click into it and we'll see. Basically, it looks like it's getting a list of processes from the operating system, and then it's going to search for those. It's going to pass the processes as an argument to search assemblies and search services. And the output of that is going to influence the return value of track processes. And so search assemblies, let's have a look at it. We go into search assemblies. It's passed an array of processes, so the processes and services that are on the endpoint, and it's going to hash every one of them. So it's going to get the process name. It's going to hash them in their lowercase format. It's going to get that hash using that FNV algorithm we've just looked at. And then it's going to look to see whether or not that hash it's computed appears in a list, in an array called assembly timestamps. And if it does appear in that array, then that's going to influence the return value. So let's have a look. We're going to assembly timestamps, and here we've got a hard-coded list of hashes that this particular sample is looking for. We can scroll all the way down. Here's many hard-coded hashes that this particular sample is going to be checking for. This is what FireEye have been doing. So they've taken all of those strings, all of those hashes, and been able to brute force all of the kind of stuff that this is looking for. So you can see here, like it's looking for psiv, pbrowser, pview, pstudio, which we ran before as well, process hacker, process explorer, procmon, all of the sysinternal suite as well. Also looking for antivirus vendors as well. So you can see like Carbon Black, you can see CS Falcon Container, which is CrowdStrike, all this other stuff. So it's looking for monitoring tools, it's looking for antivirus tools, it's looking for any kind of tool which thinks it's in an analysis environment. So very stealthy way of checking for that, because these are not ordinary signatures that you would look for to determine that this malware is checking for this kind of behavior. So super stealthy. So that's how it's doing it. It's very clever indeed. So also to note as well, let's go back a little bit in our code. So we're up here, track processes. So let's presume that it doesn't find any of those monitoring tools running. It's going to do all of this stuff down here. And actually, when you scroll through the code, I mean, as I say, we're not going to analyze every single line of this, but as you scroll through the code, you'll see some of these strings as well, these base 64 encoded strings here. And there's a lot of them throughout this code. I mean, as you can see in this particular example, there's quite a few here. And so what we want to do is find out what these strings equate to. So we'll take this one as a prime example. And the way I do it, I was just having a look in CyberChef, which is one of my favorite tools. And so in CyberChef, you can base 64. There we go. But you'll notice that it's a load of gobbledygook. And it's actually, if we find this base 64 string, you can see it's been passed. Each one is passed to this unzip function. Again, clicking unzip, you can see what it's doing. Checks to see whether it's not an empty string. It's doing the conversion from base 64, but it's also decompressing the string as well. So we need to do that as well. We need to inflate it. And in here, it's called raw inflate. If you raw inflate it, there you get the true string. So select star from Win32 network adapter configuration where IP enabled equals true. And again, you can go through the rest of the code and you can pluck out all of the other stuff that's of interest to you as well. Let's go back here. So that's pretty cool. Lots of stuff to get your teeth into here. And the function names, I would imagine, do probably map to roughly what the logic within the functions relate to. So get OS version, it probably is getting the OS version, and no doubt it's piping it back to the actual bad guys as well. Just going back now, so we looked at get OS version and all this other stuff around here. One of the questions that I've been asked quite frequently is, well, what does this malware do if it finds one of the processes that are on the list from FireEye? So what happens if it finds one of these services or processes running? Well, it's a great question. And so let's take a step back a little bit. So we'll rewind. So we went into this update process, and then we've got this track processes call as well, where it sits in this while loop to look for whether any of these processes exist before it goes off and does all of this stuff here. So we go back into track processes, and we can see there's a couple of calls here. So the first is it gets all of the processes by a call to get processes. And then it does a search for in search assemblies, where we looked before. In search assemblies, it's going to look for those processes names against those hard-coded strings in the search assemblies array. But also, it's got a call here to search services, and it passes the processes through as well. And so we'll have a look at search services in a bit more detail. We can see here, again, loops through the length of the processes array, and it takes each process in the array, gets the hash, okay, just stores it in a variable called hash, and it looks to see whether or not a hash exists in another hard-coded list here in timestamps. So we'll come back here. So if it exists in timestamps does not equal -1, i.e. if something exists, then the next thing it's going to do here, it's going to look to see whether or not it can change a registry key and stop the actual service from running. And the way it's going to do that, and you can see here, that also tries to keep a track of whether that is successful by modifying some variables, some Boolean variables to keep track of stuff, which then get used later in the code. But it's all done by this set manual mode. And this is, I'm presuming, manually setting the mode of a service is probably the logic in what they're calling it there. And so if we click into set manual mode, we can see here, takes in the array service list array, and it loops over those. We got in a try catch block, and so we can see here it's using a registry key. It's going to open a sub key, and it's base 64 encoded as well. So we need to use our little formula in CyberChef to work out what this is. We'll put it in there. So system control set services. Okay, so for each string text in those sub key names, it's going to look for the services. It's going to get the hash from that particular array that we're looking at. If the service is started, then it's going to set the key permissions to false by the looks of things. And then also as well, let's just decode what this says here. This particular base 64 encoded string, it's going to set the start subkey, and it's going to set that value. And you can see here that it's going to set it to the number 4. And so if you to do a bit of Googling or do a bit of research, you would find that by doing that, that actually disables, that's the number 4 there is the value to disable the particular service within the registry. So presumably the next time that machine boots, that service is going to be set to manual mode and set to disabled within the registry, and therefore not start. And then hopefully the initial while loop that we were looking at just before would then find that that process is not running, and then all of the rest of the bad stuff can happen. So super stealthy. I mean, that's not the noisiest way to stop a service, because it, to me, would rely on a reboot of the server. But very, very stealthy, very clever, very well written. And as I say, it's blending into the rest of the code here. Now, you might also want to know what's next. What can this malware actually do? So if it finds a service, it's going to try and stop the service from running, that it doesn't want to be on the machine. But then what can it actually do? What are the functions of this malware? And what is the intention of it? And the reality is, if I'm honest, I've not analyzed it all. I don't know. But if you look at the research that FireEye have done, and you look at all of the other stuff out there, and actually if you look through the code, if you take a cursory glance through, my opinion is this is a very sophisticated backdoor. It's going to provide access, it's going to provide information back to the bad guy about the host it's running on and all of the stuff that's going on the machine, etc. But I feels like it's the first stage of something for me here, that it's ready to drop something. It can run a file, it can delete a file, it can stop a service, it can do all of this stuff, which is definitely bad, but it's not too malicious that it's not destructive, it's not ransomware, it's not a wiper malware or anything like that. It's very stealthy and very geared around surveillance or that kind of reconnaissance espionage. This is that kind of level of code that we're dealing with here. That said, you can definitely get a feel for what this is designed to do. If we have a look more around the code to do with the communication back to the C2. Now, you can follow the code as we've been jumping in here, clicking into different functions and seeing where it takes you. You can also use the analyzer as well, which I've already shown you, which is really useful to see what method is called by what function, etc., etc. Really, really useful to dive down that rabbit hole. And you can also clear this out as well to save it getting too noisy. But really, for me, I like to just follow my nose a little bit, and I don't like to analyze code line by line. I like to see interesting things that stick out at me. And if I have a look down here, I see stuff like strings being declared. These domains, domain 3, domain 4, etc. And they're base 64 encoded with that raw inflate thing we have to do. And so the bad guy doesn't want me to know what this is, which just makes me want to know what it is. So I modified our CyberChef recipe a little bit here, just to add in a regular expression to pluck out. We can copy and paste multiple values, and it will pluck out the base 64 for us, and it will decode it. So EU West 1, etc. is domain 2. Let's have a look and see what's in here. AppSync APIs. This is part of like the actual C2 domain that has been reported by FireEye, and we can see avsvmcloud.com as well. So that's stuff that's interesting to me. I found now where the C2 is being referenced, and we can use this analyze feature again to see where this particular string is being read. And you can see it's being read in this crypto helper get status function here. So we could dive into that, and we can see that get status just returns a concatenated string of domain 2, domain 3, it's going to select 1, and domain 1. And so if we go back, what was domain 2 again? Go back in here, AppSync dash API, and then it's going to concatenate it with one of the domain 3 dash EU West 1, whatever it was, and then the avsvmcloud.com. So that's how it's building the C2 domain and subdomain. So that's pretty interesting. And again, it's all about just scrolling through the code to see what stands out at you that you think is interesting. If you want to start diving into the malware C2 communications, well, let's have a look and see what get status is used by. And we can see it's being used by these strings. So get current string here. Get current string is used by this update function, which is what we saw earlier on before, after it tracks processes, etc. So this is where, so you can see host name is being generated, which is essentially what we just seen there. I start going down the rabbit hole. And as I say, the idea of this video is not to go down that rabbit hole with you completely, but to show you the way of, the tools and the tactics and the methodologies and the approach that you should take. Now, one thing I'll also mention, we'll just go back to the countermeasures here. All of these hashes, these hard-coded hashes here, the FireEye have done a fantastic job in analyzing and bringing to life what all of these hard-coded hashes mean, so we know what the bad guys are looking for. What I did do is just take a look. I extracted all of the hard-coded stuff from this particular code into a list myself. And so let's go to our terminal window here. And so let me remind myself what I called it, hard-coded hashes. So all of the hard-coded hashes that appear in the particular code. And also I wrote a little bit of Go. Again, I'm not a professional developer by any stretch of the imagination, but a little bit of Go which just replicates that particular hashing function. So you can feed this code. So we'll just run it, and you can feed it any kind of string. You spell it wrong, and it will generate that FNV1 hash for you. But also, if you feed it a big list like this, it will hash them all, and it will mark it as green if it finds a function name that you feed it that appears in that hard-coded list. And there's quite a few people now who have found items in the list that FireEye have yet to get round to. So if you do want to contribute to the community and crack a few of these hashes, I'll put the link in the description of this video to the GitHub repo where I'm hosting this code. Feel free to get involved. Well, all right, guys, there you have it. We've had a real good look there at what this nation state malware looks like. Super complicated, very well written, super stealthy. There is tons of code to analyze there, but definitely follow the research that FireEye have done. There's other companies as well and other blogs that I will link in the description of this video that would no doubt help you in your analysis. If you're dealing with an instant response situation as well, the US government has put out some fantastic guidance. So have the National Cybersecurity Centre here in the UK as well. There's lots of resources out there to help you. But hopefully, if you're picking apart this malware, you've learned something new and you can apply it next time you're in this kind of situation, looking at this kind of sample. And hopefully you've learned some new tools and tactics that are going to benefit you, level up your game. And make sure that if you find something interesting, that you share it with the community as well. And we're all super interested to know what you find. Please share your research, because without that, we may not all learn, grow and develop together. So please get involved. Thanks very much for watching the video. If you like it, please hit the like button. If you like what you see as well, please subscribe to my channel. It really does mean a lot to me. And I absolutely love your questions, your comments and feedback. And please follow me on Twitter as well. You can find me at CyberCDH. And I really look forward to it. Thanks, guys.